A solar cell consists of a thin, flat wafer of P-type semiconductor on which a very thin layer of N-type semiconductor is grown to create a p-n junction with a large surface area. The back of the P side is coated with a metal to form a metallic back contact. The top of the N side is provided with a metallic grid contact that covers only a small percentage of the total exposed area of the cell. A solar cell works when light is incident on it from the top over the N side of the device. A solar cell works on the same principle as that of a photodiode, where incident light generates electron-hole pairs in the depletion region of the p-n junction. As in a photodiode, the holes are pushed towards the P side and electrons are pushed towards the N side due to the electric field in the depletion region of the solar cell. The holes pushed towards the P side are collected by the back contact, while the electrons pushed towards the N side are collected by the grid contact. This collection of charges makes the back contact positive and the grid contact negative, and gives rise to a current when a load is connected between the two. Unlike a photodiode, a solar cell works without any external bias. The large surface area of the p-n junction in a solar cell generates measurable photocurrent, making it a source of electricity. However, just like a photodiode, the photocurrent produced by a solar cell depends on the intensity of the incident light. If we plot the intensity of solar radiation against its energy, we find that the maximum intensity radiation is produced by photons having energy equivalent to 1.5 electron volts. Thus, semiconductors having band gaps lower than 1.5 electron volts are used in the manufacturing of solar cells. Here are a few examples. In semiconductors having band gaps higher than 1.5 electron volts, only a small portion of the total solar radiation is used to produce photocurrent. Thus, such materials are not preferred in the making of the solar cells. In semiconductors having band gaps much lower than 1.5 electron volts, most of the incident radiation is absorbed by the top layer of the cell. Thus, very little radiation reaches the depletion region to produce electron-hole pairs that gives rise to the photocurrent. Hence, such materials are also not preferred in the making of the solar cells. Besides band gap, the other criteria for selection of suitable material for solar cells include high solar radiation absorption capability, good electrical conductivity, and ease of availability and cost. Here, we can see the IV characteristic of a solar cell, which is drawn in the fourth quadrant, as it does not require any external bias and acts as a source of electricity.